quickly start where we left off, continue from where we left off. But what I'm going to do is I'm going to answer one question. There is a question by some guy. Mustafa is asking, can I use a scanf to actually read something like this? So I want to read, let's say 1, 2, 3, 4, something like this. So this is his question. All right. And he wants to use scanf, assuming that, let's say your S is, let's say there is a function integer f. So there's a block of code here, and character S is, let's say, this guy. And he wants to read this one using the numbers using, let's say integer, I don't know, I, and he wanna do this one, a scanf as format and I, and he's saying, okay, I know how to do this. If I actually, let's say S1 and S2, and S1 is only separated with, let's say, spaces like this, and S2 is this, I know that S1 will read this number. So if I call as this thing, this one is gonna read number I, the number 1. So this one. And if I actually call the same thing with S2, this will return in I, return I equals 1. This will return after this, of course, return I 1 as well. Now, question is, if I call this one more time, this scanf one more time, of course, I need to do something like that, right? So if I want to call this one more time, I know that S2, this line of code is going to return I2. This is fine. Now, what is going to happen to this guy? Is this going to return 2 or what? So this is the question that Mustafa is asking. Anybody? Can anybody tell me what should be the answer here to this thing? So at line 20 here, let me put it this way. And where is this guy here? At line 20 here, if I say scanf S2 with this guy, would I return 2? So S2 is here. I first read this guy, and then now I am trying to read again one more time from this S2. All right. So would this actually work? So if you recall, this is the right. J. So this will return I1 and J2. Question is, what would happen if I do this one? So what would happen if I use a scanf S2 reading 2 integers? Would this be 2 or what? So this is the question. Someone tell me. Anybody? Wake up. Anybody?
Hocam sanırım mesajlarımız yine gitmiyor size.
Gitmiyor mu? O zaman söyleyin, biriniz söyleyin. Ne oldu? Niye gitmedi bu mesajlar? Ha yok, gidiyormuş, buradaymış. Okay. Hepsinde ilk değeri vermez mi? So this is gonna be okay. But why is this gonna be 2? So what is the difference between these two? Why would I think that actually it will be both giving me I equals 1 and J equals 2? So that means that doesn't this make any difference at all here, that comma? The question answer is it should make a difference. It doesn't make sense if it doesn't make a difference, right? So what is going to be the difference? If you recall what I actually told you during like a couple of weeks, like 4 weeks or 5 weeks ago, this is going to read an integer. It's going to say, okay, I start from here, I read an integer, and I'm done reading, and now I am here. I hope you are seeing where my cursor is here. This is the line 18, okay? And then I say, okay, read me another integer. It says, read me another integer. But at this location here, there is no more integers. Okay, what may happen? What may happen is that since this white spaces cannot be consumed by scanf. White spaces can be consumed by scanf, but anything other than white spaces cannot be consumed by it. Meaning the reading is gonna be stuck at that period, so comma, right? So I'm gonna be there, and I'm asking it to read another integer, and it's gonna try to read something. It's not gonna make any sense. All right. So I don't know what it is gonna read. I know what it is gonna read, but it's not gonna be 2. I am sure of that. It's not gonna be 2 as you would expect. Actually, you wouldn't expect 2. So it will be some garbage number that it's not gonna make any sense. So what do we do in this case? How do we actually do this? There are 2 possibilities, right? So what I can do is I can say I will split this line into 2 pieces. I'm gonna read, let's say, the first character, first number, right? And I'm gonna know how many, so once the first thing is read, I can move my, let's say, in this case, I know that if I actually start from reading, for example, from this, like this, now I can read J to be 2. The first one is gonna read the J, right? And this is 2. This is one possibility. What did I do? What I did is I looked at my number and I know that my text or my string, I know that the first number is 1 character long. All right. So I will read my first number and then I will move to, I need to actually skip this guy. I want to skip this guy because if I don't skip it, it will not read anything useful to me. So what I want to do is I want to skip. How can I skip it? I know that the character after this one is actually here, this one here. So this is the 0th character is 1. This first character, index 0 is 1. Index 1 is comma. Index 2 is, which is this guy, which is the white space after the comma. Now, after that white space, I can read now 2. Okay, so this is suggesting you hopefully a solution. And I'm gonna stop here because if I actually do the rest of it, I think I'm gonna be solving the homework for you. All right. Okay, I hope Mustafa got an answer for his question. All right. Okay, let's go back to what we were doing. So we were trying to actually see what type of problems do we have that we can actually split into, let's say, this size n is given as n size problem, size n problem. I want to actually make sure that there is a simple size 1 problem plus a size n minus 1 problem. So can I actually, what can I do? Which problems can I actually solve this way? For example, let's look at one case. What I want to do is, let's think about multiplications, right? In principle, a multiplication, let's say, if I am, let's say, multiplying, let's say, n times m, the definition of this multiplication in terms of a basic operation, let's say, addition. Just, I want to use additions to actually do this multiplication. So if you know that n times m, it can be actually written as n plus I want to actually do m times this operation, right? N times. This is the multiplication in terms of addition, right? So multiplication is actually a short hand for addition. If I am multiplying a number n with m, what I mean is that I am actually adding n 10 m times, or I am adding m n times. So this is n times here. So m times, or adding m n times. So this is the definition of actual multiplication, right? Very simple. Then I can easily tell you the answer to this one. I can write a function. Is if you give me a function. So if you give me two numbers to multiply, fn and m, this is simply this. The answer is n if m equals 1. If m is 1, if your second number is 1, the answer is simply 1, n, right? Because 1 times n is, you are adding n one time only, okay? If m is bigger than n to 1, so what do? You actually do it this way. You say, okay, I want to do an addition of n with what? Fn m minus 1. So I'll call f function with 1 less, meaning I take this part of the addition, and then I have a simple, so this is the simplest part. Add n to something, and this next something is actually the size n minus 1 problem. A simpler or a smaller problem. Or did I start recording? Let me see. I want to make sure that I am recording. Yeah, I'm recording. Panicking. All right. So you see that now I can actually in principle, this is a simple thing. Of course, I'm not going to do it this way, but an addition or multiplication in terms of addition can be actually expressed as a simple recursion. And the recursion is, again, if I write it here, given n and m, the answer is n if m is 1. Otherwise, n plus f of n and m minus 1 if n is bigger than 1. This is the thing. And then now the coding, this one is very, very simple. The coding is, in this case, I have n times m. If n is 1, the answer is m. Otherwise, the answer is n plus the n minus 1 of those m's. So very, very simple. And the answer is that. All right, very, very simple one. This is a very simple recursion. So a multiplication can be decomposed into simple additions, and n times adding something with together. I mean, adding n times means add that number to a subproblem where you do this n minus 1 times. So this is the n minus 1 times. You do this one, and then this is the basic thing, and the nth one is when you have only one of those m's to add, then you just return that number. So this is a very simple recursive function for multiplying two numbers. Of course, this is not a useful thing. You know that I achieved this one by this anyway, right? So why do I care about this one? This is just to illustrate the point. So let's look at maybe a little bit more, let's say, or this is for illustration purposes, we are going to see better problems to be solved using these techniques, or more meaningful problems. But if you see, let's say, how this function is going to be tracing, let's say, so what I am going to do is, if I am actually asking you to do multiplies 6 times 3. So m is 6 and n is 3. Now what do I do is I'm checking if 3 is 1. No, here I'm checking if 3 is 1. So if you recall my thing, function, what was a function here? So let's go back to here. So you can see that I am checking if n is 1, the answer is m. If n is not 1, the answer is, assuming that m is bigger than, n is bigger than 1 or 0, then the answer is actually n minus 1 times m plus m. So here 3 is not equal to 1. Therefore, I am going to actually call 6, m is 6 plus the smaller problem. And the smaller problem now is here. Now it is 6 times 2. 2 is not 1 still. Therefore, I'm going to actually do an elemental problem of 6 added by this guy, 1 minus 1, n minus 1 size n minus 1 problem, which n was 2, now it is 1. So this actually goes to this problem. Now this problem has n equals 1. Since n is 1, then my answer is going to be just 6 itself. And then I take this 6 back here. Now 6 plus 6 is 12. I take 12 back here. And 6 plus 12 is 18. I return you the number 18. Very simple, right? So this will be, for example, multiplying 8 by 3. This will actually iterate 3 times, right? For n3 and then n2, and then n1 is gonna actually stop the recursion. It's gonna hit the base condition. This is our base condition here, and then it's gonna continue going back and actually collecting the results as it goes back, as we see here. This is actually collecting the results. So when it reaches the end, it collects the results here in the first call, and then it collects the results here in the second call, and then collects the results in the first call. So the third call, this is first call here, this is second call, this is third call, and this is the fourth call. So fourth call is not gonna go because n is 1. It will return the collect value of 6, and then the third call is going to return 6. The second call is going to return 12, and the first call is going to return 18. All right. With another problem, let's see what else can we do with recursions. Let's assume that I have a problem as a string operation. I want to do a function. And I want to count the number of s's in a given string. Let's say in this case, you have this string, Mississippi, sassafras, whatever, right? And I want to count how many s's are there. So what is my basic problem? My basic problem is, again, I'm going to go back to this guy here. So what I want to do is I want to count the s's in, let's say, number of s's in Mississippi, right? Mississippi, or I don't know, maybe I did it wrong, right? So size m problems is actually the entire string. I'm going to take my entire string. This is my size m problem. So let's do this one. Let's say miss. This is the string. Size m problem is the entire thing. It says split your size m problem into 2 pieces. First, the size 1 problem. In this case, what I'm going to do is I'm going to take the first character out of here. So let's do it this way. Get the first character and solve that for first character, meaning the size 1 problem is I will take my first character, m. I'm going to say, is this m s? Is an s? No, the first character is not an s. Therefore, I'm not going to count anything. If it is an s, I'm going to count something. So this is the first problem. The size 1 problem is if, let's say, the first character is an s, just increment it by 1 your counter, else do nothing. Do nothing, right? So this is it. Then my size n1 problem is simply the rest of my string. Do this for the rest of the string. Okay. Now I have a function, actually, it's a very simple recursive function. The recursive function is going to be something like this. F of string, I will take the string. It says, let's do it this way. My f string given the string is going to be this way. Return, let's say, so if size of s, this is the size n problem, this is n, is 1 and the string equals s, so let's call this str. Size str is 1 and str is s, then return 1. Else, if size str is still 1 and str is not an s character, then return 0. Otherwise, else, do it this way. What you will do, depending on actually this thing or this thing, you would call if else is s is str is s, str the first character is s, then do 1 plus f str rest, and otherwise do it 0 plus f str rest. So this function is gonna be simply this. So what am I gonna do? I'm gonna say, okay, if you don't have anything left to solve, meaning my sub problem, the current problem is an empty string. I know that an empty string doesn't have anything in it. Neither s nor something else. So I can return safely 0. Otherwise, I will check if my current first character, so this is the character that I am looking for, this is the s. My search character is the same as the first character in that string. If that is the case, I will add 1 to the subproblem. Subproblem is I'm taking the str, the string, and I'm continuing on the second character, not the first one. So if I have this miss, for example, what will happen is that you can see that if str is this, str0 is gonna be n, character m. str1 is gonna be character I, and the address of str1 is gonna be given me the string ISS like this. So the second character, so the index this will give me this character. If I want to look at the address of that thing, then I will get the rest of the string here. All right, we have seen these examples in our string operations before. So now, in that case, my problem actually starts become very easy. This is my base case where there is nothing in the string, therefore the answer is simple 0. There is something in the string. The first character, if the first character is the character that I'm searching for, then I will call the rest of the string, excluding the first character, plus 1. If the first character is not the one that I'm searching for, then I will just call the rest of the string, excluding the first character, as an answer. So this way, if I have, let's say, this guy here searching for, this is ugly. So if I am searching for S in this, so when it is here, this first one, it's gonna be calling this guy with what? With SS. Okay. In the second iteration, when I go into this guy, now my answer is, my actual string is simply this guy, right? So now, since I is still not the character that I'm searching for, then I'm gonna go for this guy one more time, right? So now my substring is gonna be just simply SS. The rest of the string is gonna be SS. And I'm gonna calling this guy with SS, of course, right? So here, just with an with SS. And then when I call this with an SS, I will hit, I'm not hitting here, I will hit this guy. I'll say 1 plus the rest of the thing. The rest of the thing is gonna be simply just a string with S, just single S character, right? And then when I actually call this with this one without this guy, then I'll get to here again one more time. So this will be 1 plus 1 and this guy. Now this guy is gonna say, okay, it is empty because the rest of the thing of this thing will be just an empty string. And the empty string is gonna hit here and it's gonna return 0. So I will actually have 0 plus 1 plus 1 plus 0 for the I and plus 0 for the M. So this will be my answer. My answer is gonna be 2 for searching character S in miss, M-I-S-S. So you can see that now I can use, in principle, a recursive call to do a simple counting of this sort. Okay, you may ask, oh, we could have done it with using a simple counter, right? Counting loop. Of course, you could have done it with a simple counting loop. It would have been much easier. But just to prove that you can do it with a recursion, it will be here. So nobody would probably count the number of characters in a string using a recursion. Loops will be faster, but there will be other problems that could be solved much easier using a recursion rather than, let's say, instead of a loop or counting loop. So let's look at another case. What I want to do is, this is a simple example. I would actually read something from the user as a word, just a single word, okay? And I will reverse print it. So if my input is, let's say, if I'm gonna input, I don't know, let's say A, B, C, D, E, F, your code is gonna actually reverse this with F, E, D, C, B, and A. This is what I wanna do, right? So thinking of actually this same approach, do a simple problem first and do the, let's say, do the n-1 size problem. So here, what I am doing is I have this reverse input function. And I am saying, okay, I will read the words. And if n is 1, then what I am gonna do is I'm gonna actually just print that if n is less than 1. Okay. This is the base condition, right? Otherwise, I'm gonna read the and I'm gonna actually reverse input the n-1 part of the thing. So I will actually, this is wrong, I'm sorry. This is not the problem that we are trying to solve. We are trying to solve this problem. So let's go back. So the user is gonna enter, let's say, what you wanna do is, user is gonna enter, let's say, word 1, word 2, word 3, word 4, and the output is gonna be simply this. Word 4, word 3, word 2, and word 1. So This is what we are gonna do. So you are gonna ask user, enter something here 4 times. Okay. So I'm gonna read 4 words from you like this, and then I'm gonna reverse order them and print them. Now you can see here that what I'm doing is if you read only 1 word, meaning this guy here, I will just print that word for you. You read it, you print it if it is 1 word that you are reading. If you are reading 2 words like this, do the last one first, and then the second one, the first one second, and so forth. So the simple problem is, what I do is, I say, okay, I'm gonna read 10 words. Let's say 10 words. I will read your first word, okay, and then I'm gonna say, okay, call the same function for 9 times, doing this 9 for the last 9 words, and then call the same function using 8 words for 8 words, then 7 words, then 6 and 4, 5 and 4 and 3 and 2, and then when it's actually reading 1, then I actually just print that. Now you can see that I am not actually, if I were to give you with the, if you were to actually do this problem with a loop, what you would need is actually here, you need to store each of these words. So you will read the first word, store it in an array, the second word, store it in an array, the third one, the fourth one, and then do a reverse order printing. Now here you can see that I have no need for actual storage of any kind. So how did this happen? Of course, there is a storage, but the storage is actually happening when I call this function. I already actually got the current word here. I'm keeping in my mind, and I'm letting the rest of the n-1 of those words to be printed in reverse order, and then I am actually printing it. So in principle, I'm actually keeping it, but not explicitly in an array, but implicitly in each recursive calls memory space, right? So this is a good example where now counting loop would require you to actually have a 2-dimensional array or array of strings, and then store them in the array of strings and then print them in reverse order. Here, instead, I don't need that array. I will do that storage by just looking at each function call and keeping the current word locally in that function call, and then go for the smaller problem, and smaller problem till I hit the last problem here. So any questions? This is a little bit difficult to understand, but we are gonna actually do an example of this one. So I'm asking you to actually enter 3 words. So what do? I say, okay, ask the person to actually read the first word, type the first word. Let's say I said, let's say this, right? Now, this is actually kept in this one here. If you look at this guy here, this is gonna be kept here in Word. Then, okay, I call this function again the same function, but this time say, okay, read 2 words instead of 3 words. Okay. Now this function comes and says, okay, read the second word. Now this one is stored in Word when the function is called with n, right? Now you enter the second word. So the second word is, let's say, this is. Now I am here. And now this is going to be stored in Word. This is n is 3. Now n is 2. It will be stored for the function in the function that is called for n equals 2, right? And then in turn, it's going to say, okay, call the same function again, since I haven't reached the 1 case, one more time. In this case, it's going to say, okay, read another word. This is it, let's say, right? Now, this one is the last one, n is 1. Now it is gonna print it out. So print it, it is printed, right? And then I am done here. So the function says if n is 1, just read it, print it, and then forget about it. Okay, I read it here. I read it, I printed it, and then I forgot about it. And then I return to my calling function. Calling function is this guy. This guy has the word is. Then print that word, it says here, after the call is returned here, print the word that you have kept, which is, and I actually print that is here. Is printed. And then once it is printed, it says return back to, so once it is printed, return back to your caller. Again, now it is N3. N3 is this guy. Hold on. N3 is this guy, and N3 actually read this, and it will print this. And then it was the first call to the recursive function, and it will actually return out of the function. And then this means that these are the input that I actually gave, and this is the output that I got. So the input was this is it, the output is it is this. So I, in fact, did the desired thing by ordering or the reverse printing the inputs read from the user for each line. This is very good. This is a very good one. You can see that there is no storage here for reading all the lines of words that the user is going to actually input. How did I achieve that? Again, for each call, there is this word, and then I'm actually putting that word out after the function, smaller function or smaller problem is solved. This is reading, this is a larger portion of the problem. Read the word, smaller portion, let's handle it, assume that it is handled inside there, and then just print it. If this is properly done, then this would actually just print the first word as the last one. All right. So this is actually quite powerful now. This means that now without actually the need for, let's say, if I needed to do this with a, let's actually do that. If I want to do this as a iterative one, this is what I need to do. So let's look at it here. So the iterative function, let's say void, what was the function? Reverse print, right? Reverse print integer n. And I have my character word, some size, doesn't matter, right? And then I will have integer I for my counter. And then I will say for I from 0 to I is less than n, I plus plus, scanf, right? I need to read. What do I read? I need this guy. Where do I read it? I read it to a word. Now, of course, this is not gonna keep it. And then once I actually done this one, if I have done it this correctly, then I will actually print. So this is the reverse order print. I will start from n minus 1. I will go till I is 0, I is less than, greater than 0. And this is gonna be I minus 1. Then I will just printf the word. Of course, this is not gonna work because I need to actually store each of these words. Therefore, what I'm gonna do is I'm gonna have perhaps at least, let's say, 10 words like this, right? And then I will start saying that this is the word that I'm gonna read, and this is the word that I'm gonna actually write in the reverse order. You can see that I have now, I need to actually declare this guy, and then I need to actually declare another variable for counting, and I will do two loops. First, reading each word from the user, one at a time, and put them in order, and then another loop that actually reverse prints those. Start from the last one, print the last one first, and then so forth. Now compare this guy to this function, where you see that there is no, actually, other than just the word itself, I don't need to do any other declarations. And it is a simple one. I'm just actually saying, okay, do the base condition first, and then do the rest of it. This part of the, or the, let's say, repeating part of the, or sub problems next. All right. Questions? Any questions? We have another 12 minutes. I'm going to continue a little bit more if there are no questions at this moment. Okay. No questions. All right, good. So let's continue. This is the call sequence, and you can see that actually this is the event. If I want to actually kind of say individual sequences of actions that I actually did. So the first one is you call the reverse input words with 3, and then you scan the words. Let's say you read this one into Word, and then call the reverse input words with 2, and then now you scan end for Word. So my input is going to be here, bits and bytes, I think. All right, and then I will call the reverse the same function with only 1. Now when there is 1, it will read this guy, it will print it, it will read it, it will print it, it will return the third call, which is gonna be this guy here. Now it will print display the thing, which is, it will display, it will return the second call. The second call was bits, it will print bits, and it will return the original call, which will be done. So bits and bytes actually reverse to bytes and bits. All right, good. So this is a good way of actually tracing the sequence of events, the sequence of actions. If individual statements in the call is here, let's say these individual things scanning. So this is one action. So I'm in the wrong place. This is one action, this is another action, this is one action, another action, another action. So, all right, good. So let's see another example. Factorial, we have seen this one. It was a very simple one. If n is 0, my answer is 1. If otherwise, assuming that n is always bigger than 0 or equal to 0, larger than or equal to 0, then answer is n times the smaller problem, n minus 1 size problem. And when we look at actually the tracing of this thing, if you call factorial 3 is going to say, okay, is n 3? No. Then call 3 times factorial 2. Is this guy? Is n 2? Then call 2 times the factorial 1, right? And factorial 1 is this guy. Is n is 1? Yes. Sorry, no. This is 1 times factorial 0. Now factorial 0 is this guy. Is n is 0, which is, again, if you look at here, we are checking n 0. If n is 0, yes, then return 1. This will return 1 here for this guy. This is 1 times 1 returns 1 again. 2 times 1 returns 2 here. And then 3 times 2 is 6. And the answer, your answer is going to be 6. This is how you can trace your factorial function. Okay. Let's say the iterative version of the factorial function will be this one. You'll have an iterative counter, and then the product itself, you're going to keep the product 2 variables, and you're going to do a from n to 1, decrementing I by 1. You will actually do a product times n. So this is, and then return the product. So you see that these two calls actually are different. One of them requires you to have these counting variables and the resulting accumulate. And in the other one, I don't have a need for any accumulator here. I need only, and I have this answer. This is just for our readability purposes. I would have actually just returned here. This is what I don't want you to do, but you can do it this way. So you can actually return just this guy. Therefore, you don't even need this one, perhaps, right? So this is a very, very simple code now. You have actually 2 lines of code. If something return this, else do this, right? Whereas you have to get your local variables in order, counting variables and counting variable, as well as your accumulator, do a for loop, accumulating the results and then returning the results. So recursive functions could be sometimes much simpler to write, and it may be also quite easy to read as well. Okay. All right. This is the Fibonacci numbers, right? So you have, if n is 1 or n is 2, then the answer is 1. Otherwise, answer is actually Fibonacci number, Fibonacci n minus 2 and Fibonacci n minus 1. That's it. Very simple one. Let's look at another one. This is a problem that we know. For example, what we are trying to do is finding the greatest common divisor of m and n. Let me ask you, what is the greatest common divisor of 10 and 5? M is 10 and n is 5. Someone answer me. What is the greatest divisor of what do I do? 10 and 5. Someone stop sleeping. I think you're 5. Okay. Anybody else? Yeah, the answer is 5. So how are we going to do this one? Let's look at the recursive function. Recursive function says, okay, what are we trying to do? We are trying to find some number that actually can divide. So let's look at it this way. If n divides m, right? If n divides m, then we can easily say that n is our GCD, right? If m divides n, then we say, okay, n is the GCD. If not, then what do we do? For example, let's say 12 and I don't know what, 20, or not, let's say 20 and 12, right? What is the greatest common divisor of 20 and 12? Someone? 20 and 12. 4. All right, good answer. So how are we going to do this one? We are going to say, okay, you can say that, okay, if this number doesn't divide this number, then what can we do? We can look at actually this thing. We can say, okay, now look at the remainder of actually what I would do if, let's say, I divide, let's say, m by n. So this is the one that I'm looking at. And replace this one. So it says, this is what we are trying to do. We say, okay, my subproblem becomes here this way. Take 12 as the first number now, and then see if this is divisible by 20 divided by 12, the remainder of 20 divided by 12. So the remainder part of 20 divided by 12. Okay. The answer is going to be here, of course, is going to be 8, because this is 1 times 12 is 12, and then minus 20 is going to be 8. Now I'm going to be looking at 12 and 8. Now, is 12 and 8 actually, 12 is not divisible by 8 still. So I will do one more time, take 8 instead of 12 now, and see if this is divisible by 12 divided by 8 and remainder of that. So the mode of 12 and 8, which is gonna be 4. So this is gonna be 4. Now we are gonna say, okay, is 8 divisible by 4? Yes, and this is my answer. So what we did is we actually defined the problem such that if m is divisible by n, then the answer is n. N is the answer, assuming that they are, let's say, m is greater than n. No, sorry, m and n are both larger than 0. Okay. Otherwise, what we do is we say, okay, take n instead and look at m remainder m divided by n remainder. Whatever actually is left off after dividing m by n. So in this case, this is working. So what if I actually reverse order these two? Let's look at this one. Instead of looking at 20 and 12, which seems to be working. Now let's look at actually 12 and 20. So I have 12 and 20. So I look at this one. I say, okay, m is this is m. Again, this is n, right? Now m is not divisible by n. You cannot divide 12 by 20. So what do? You put this one here, 20, and then you change n to be what? You say, okay, 12 divided by 20 remainder. Since 20 is bigger than 12, the remainder is going to be the number itself. So this is actually a simple way of swapping these numbers or ordering these numbers. All right. Now this becomes the same problem that I have actually solved just a moment ago. The answer is going to be, after the third iteration, it's going to be 4. All right. Questions? Any questions? So we are going to talk about this a little bit further. This is I mean, without knowing this algorithm, of course, you are not going to be able to write this recursion equation, but people have known this algorithm for a while. And if the algorithm is there, I can actually easily write it in that form, as we have seen here. So we'll continue with recursions tomorrow. And if you don't have any other questions for the time being, let's wrap it. Let's stop it here, and I'll talk to you tomorrow at 1:30. Okay, I'm stopping recording.